So as the title suggested, Tom Ziemke kindly already hinted, this will be a talk a little bit more about theory, concepts, and has a little bit the ambition of making the link between the kinds of things Tom reviewed about what embodiment means for natural cognition, looking at the consequences of that for how to design cognitive systems, artificial cognitive systems, although I will really be more grounded in cognition and psychology than in engineering here. What I want to do is actually spend the first part, maybe a little less than half of the talk, on a more general conceptual discussion about what embodiment means for me then, and what the implications are, the conceptual implications are for that. With a little bit the spirit that this meeting is about that, making an assessment of this concept of embodiment. And that will naturally have manipulated that so that it naturally leads to the theory addressing, of course, exactly those issues, not quite neutrally here. And so the second half would be about the theory and about a few exemplary examples that I'll take you through. I want to start by acknowledging my collaborators, because in the heat of the moment I'll forget that. A lot of people have contributed to that research program. I've worked extensively with developmental psychologists, John Spencer, Esther Thielen, who's unfortunately passed away some years ago, Linda Smith. The work from my own group that I'll refer explicitly to are these five, is the work of these five individuals: Christian Faubel, John Lipinski, Julia Sandemiska, who's actually at the meeting, Sebastian Schneegans, and Stefan Ziegler. So if we start by asking again, we've discussed this a couple of times, what embodiment actually means. What does it mean to have embodied cognition? And I always like the soccer example, so I'll take that again. You can present that in two ways. You can present that as saying, what about soccer is cognitive? Or you can say, what about cognition is embodied? Here I'll think about what about soccer is cognitive. It's clear, if you think about soccer a little bit, clear that there is a lot of non-trivial perception here. You'd have to categorize objects as other players, the ball, the goal. If you play in the wild, you have to perceive the terrain, obstacles in the terrain, and so on. You'll have to select the target of your attention, the target of your action, which will be the ball or other players or whatever it is. Control your gaze. If you want to sample the scene, you'll have to use your working memory to effectively direct your gaze, not search each time for where the goal is, but to very quickly find the goal by directing your gaze at where you estimate the goal must be based on where it previously was. So it's an important theme that I'll come back to. You'll have to control your motion. This involves not just motor control, but decisions like initiating action, maybe terminating or abandoning action in some cases. You'll do movement planning, but that planning will be continuously online. You will be updating it all the time when the scene changes, very dynamic scene. You learn. You can't prevent yourself from learning. You always get better at it. My kids got a lot better since then. It's a skill in itself, of course. And then there is this other thing, this background knowledge, as Sean Searle has called that, all that knowledge that has accumulated over the long term about knowing about grass, how slippery it is, about how hard balls are, how hard you may tackle another player, maybe tackle a little harder if it's your sister. There's a lot of graded knowledge embedded in that system that's hidden. That's much richer than just the rules of the soccer game, which my kids don't even know so well. Here another example. Driving a car is a little less motor in a way. The movement is actually kind of minimal when you have the steering wheel and the gas pedal. Maybe if you have an automatic gear shift system, it's really minimal. But it actually contains very much the same things. You have a lot of perception, scene perception, object classification, estimation about objects, all very much in real time, quite fast. Very, very, very important. You continuously update your plans. Similarly, you do make decisions, like passing decisions, maybe a braking maneuver, while you also, of course, do control. You in a graded way, control your speed, for instance. It's a skill. You get better at it as you gain experience, both perceptually and in terms of motor skills. And there's a lot of background knowledge there too. And again, it's actually not so much the traffic rules, which some of you will know, depending how many years ago you took your driver's license. But there's a lot of background knowledge about what are dangerous situations, where will you look more carefully. Italy is famous, has a very good record for not killing children, even though driving is considered not so rule-based. So there's an implicit structure that people are really very attentive to children in traffic. Now here's another example that's maybe an example where you would more traditionally think about it in a disembodied way. For instance, repairing something, a mechanical toaster. It's a photo I took off the internet. Repairing some device. That's something where we would have very much the tendency to think of that as planning, of representing the problem, devising maybe a sequence of steps that you have to make to go to the goal, and then think of the acting out of that plan as something that is maybe peripheral to that, so separate from that. And actually the text here, you ignore that. The text here argues that this is cognition, but maybe here I want to argue that yes, this is cognition, but it is actually very embodied. If you actually do that on a table, you have a lot of perceptual problems. You'll have to recognize what are screws that you can really turn off versus maybe other structures that you cannot open, other structures that you can't. As you turn this thing around, you have to track it in space. You have to make complex coordinate transformations to remember where that screw now is that you previously decided maybe to now tackle, but in the meantime you had to put the toaster down to get the screwdriver, for instance. That's a real sensory motor skill of keeping oriented relative to that object, for instance. There is compliance, control kind of skills, fiddling the screw in or out, or getting the spring back onto a lever, for instance, that you need to control, and that you also need to initiate, and maybe again abandon your attempt if something fails, and so on. Sequence generation, that you still have to remember where you are, what you were trying to achieve as you got distracted because one thing took longer. That's uses working memory for where you are in the sequence. It's a skill as well. You get better at learning, and there's a lot of background knowledge here. Actually, a lot of it is very general about knowing what screwdrivers are and what, again, how much force is normal to use, what would be destructive force you want to use, subtle sensory motor background knowledge. So these examples could be viewed as consistent with, for instance, what Tom talked about, what Pfeiffer talked about yesterday, about embodiment being cognition that involves the body. And I'm just trying to illustrate that there's a lot of cognition in there, and also that there is a lot of bodily knowledge or environmental knowledge required in this background knowledge, for instance. On the other hand, I actually would answer this question, if embodied cognition is cognition that involves the body, in the negative. I would say, no, that is not enough. That is actually just one aspect of it. And in fact, I will argue a little later that when you involve your body minimally, you will still see the signatures of embodied cognition. So that's, in a sense, a bit of a distraction that we're emphasizing the body there so much. That was important initially when this program arose. But I will argue that embodiment is actually a scientific stance. We use this somewhat grammatically, a little strangely, as saying embodiment is not about the system, but about us, the scientists, taking that stance of looking at cognition in a way in which we take certain properties of cognition seriously and think they need to be taken care of theoretically in accounting for cognition and in then generating cognition in artificial systems. And here is a summary, again, of some of the properties that I highlighted in these examples. So it's the property, for instance, that cognition involves active perception for a purpose through which perceptual objects are grounded, that we don't neglect that process of acquiring the perceptual representation, that the cognitive processes are continuously linked to the sensory surface, can be updated any times, and are linkable to motor processes. This doesn't mean that they always have to be linked to motor processes. You can look at it just as a board and just think, but you can act on it any time. You can any time point to where you're currently thinking, for instance. Which also means that the invariance and abstractions that we often think are characteristic of cognitive processes must fulfill that constraint that they can still be linkable to sensory and motor surfaces, and that actually makes it much harder to achieve these forms of invariances and abstractions. It's not just something which you can just assume and say the interface somehow delivers you the abstract thing. No, you have to have maybe the abstract representation, but also be able to go back to, for instance, pointing where in space, in which orientation that particular object that you invariantly perceived is. The embodiment stance also emphasizes the role of context, behavioral history, that cognition always comes from somewhere, goes somewhere, is context sensitive, is sensitive to the perceptual layout, the environmental context. Learning has to be, of course, part of cognition. As was asked previously, one could think of it as the core of cognition, but certainly it will mean that accounts for cognition have to be open to learning, be able to accommodate learning processes. And maybe the most general but most difficult to grasp aspect is this background knowledge idea. Minimally, it means that cognition isn't arbitrary. You can't do arbitrary things very well. There are a lot of things that, for instance, conventional computer programs do much better than we. Google is a very good example. Modern accounting systems, databases that we struggle with all the time can do a lot of things much better than we do. So there is some particular structure in our cognitive system that we're particularly adapted to that has to do with a background that we can easily acquire. And part of embodied cognition is find out about that and maybe exploit that as we build cognitive systems. So the embodiment program, this is a bit redundant, I'm just summarizing. The embodiment program is a research program in which we aim at understanding cognition in a way that doesn't ignore these things or in other words that says we have to centrally also account for those, that is for the link to the sensory and motor surfaces, the immersion in structured environments, or sometimes called situatedness. I don't use that term so much, but that's what it means. And the role of behavior history and learning and development. I personally also add the principle of understanding cognition on a neural basis. That's not universally shared in this field, but one can argue about that, and I will not now argue about it. I will just use that as a principle, and you will see that throughout, that we'll think about the constraints that arise from that fact. So the embodiment hypothesis, the sort of stronger one I was trying to make, is that these principles that I just sort of sketched apply to cognition throughout, that they don't only apply to soccer playing or only apply to these skills where the body in a very obvious way plays a big role, but that even apparently disembodied forms of cognition like thinking, reasoning, planning, language are actually of the same nature, in meaning they fulfill the same constraints. They are also processes that are linkable and linked to the sensory and motor surface anytime that use the substrate, and what Tom reviewed were some hints at that, and as he said, there are more in different domains, there are more hints of that general nature. I'll just make a very few pointers to those empirical facts. In the sense that one would think that thinking, reasoning, and so on are, in a sense, just mental action, mental movements that very much follows the same rules. And the theoretical principles we'll try to develop should thus have a continuity between, or support a continuity between these various sensory motor cognitive acts like soccer playing all the way to maybe even chess playing. So another way to put that is to say that this hypothesis says there is no particular boundary in the natural cognitive system where cognition stops being embodied and somehow becomes disembodied. And sometimes that's been asked as this question, does it have to be symbolic at some point? I don't want to put it in those terms because they don't make immediate sense, but what I want to say is there's no boundary where these principles that are listed, sensory links, learnability, immersion, behavior history, where these things don't play a role anymore. So that's a hypothesis, and I don't think we know yet what the last word on this is. Some people are still searching for niches where there would be a purely disembodied cognition, and we'll have to wait to see if they will ultimately remain, but that's where we're moving. So in the next couple of slides, I want to think a little bit about the implications of that hypothesis. And I want to point you to three conceptual steps that are very important. I will claim that from this embodiment stance flows the constraint that all cognitive processes have to have stability properties. Now I'll define what I mean by that. And then I'll next show that I will also need the opposite. We'll need the release from stability or instability. That will be really needed to do things that, like decision making. And then I'll spend a little bit of time on representation. I will put this little hyphen in here to make a point. I will actually not talk about representation as much as the title suggested. I like that a bit provocative part because I'm an embodiment person. I'm also trying to say, let's not throw out everything that we learned previously. And in reality, it will be only a part of my discourse. These first two are actually a bit more central to what I'll be arguing. So intuitively speaking, stability is the property or the capacity of a system to persist in a particular state, behavior, or in a particular process in the face of distracting factors, distractors, let's say, or in response to a phasic perturbation, recover from a phasic perturbation. That's sort of a verbal account for that. I think you all have an intuitive notion of stability. It's important that the stability is a property of a particular state, a particular behavior. It's not a property of a system per se. Engineers sometimes use it in the sense because they're often looking at systems that have one state, and then you can sort of exchange that. But if you look at systems that can have very different states, it's important to think of it as a property of a particular state. And that will be important when we look at instabilities. It will be not the whole system becomes unstable, it will be one particular state that becomes unstable. Mathematically, the property of stability can be formalized within the language of dynamical systems. It's really the property of a particular class of solutions of dynamic systems that are sometimes called attractor solutions by dynamicists. It's also what Martin Buss was referring to yesterday as a central tenet of control theory. And in control theory, you make sure that the set point becomes a stable point of your system. It's all the same concept. Here, I've sort of made a caricature of what a dynamic system is. If you've never heard about it, here's a 5-second explanation. In a dynamical system, you're thinking about a state variable. I've suggested U would be some kind of neural activation, for instance, evolving in time as governed by its rate of change. U dot is the rate of change of U, and if U dot is a function of U, you have a dynamical system. And for instance, the way activation in neural networks propagates can be described by such differential equations, which we call neurodynamics. Neural only because U is supposed to be a neural variable here. And then here is an intersection of this rate of change with the U-axis. In other words, a point where the rate of change is 0, that's a fixed point. That is, once you have this solution, your activation will stay at this value, it will no longer change. If you're to the right of this, you have a negative rate of change that will mean you will decrease following this arrow, moving toward this fixed point. If you're to the left, you have a positive rate of change, meaning you will increase. And that's why I call it an attractor. You see neighboring activation states are attracted in time toward this particular solution, a stable fixed point or an attractor solution. A very generic thing. This linear line here would be a linear approximation around the attractor. It would be the attractor would be where U is equal to H, and this would be sort of the generic form of a neurodynamic that you will find everywhere. The red line is just to show that it doesn't have to be necessarily linear. That's the generic neural formulation. I will be using this form throughout. You will see pretty much every neural network that has been looked at this way somewhere has this finds minus U term that makes a negative slope. And so it's the negative slope around the attractor that makes the stability. It's this mechanism I'm explaining, being to the right, you attract to the left, being on the left, you attract to the right. So why is stability an issue? At the level of control, so we could say every engineer knows that it's an issue. And it's easy to see intuitively when you have a sensor that's in the effector. That's the most generic way you find that in the animal kingdom. Pretty much the huge majority of animals do whole body displacements where they have the sensor in the body, and they get direct sensory feedback about their action, and they steer therefore, or can steer, very much based on just updating their motor commands based on their current sensory inputs. And think of driving a car. That's what you're doing. You're sitting in the car. Your sensor is moving with the car. You get sensory feedback about whether you're turning or not. And then you have an intuition that you need to be stable if you're not responsive enough to your sensory feedback, then you will not track the road, drive off it, or you could have the reverse, be overly sensitive and get into some kind of oscillatory instability, as happens sometimes to beginning drivers. It's maybe not by chance that in the animal kingdom this is the dominant form, because this is a form that makes very minimal demands on knowing something about the world. You could do something like visual surveying, just make sure that let's say the lane and marking on the road is in the middle of your visual array, then you're following that line. It's maybe not correct driving, but it would be an okay strategy. You don't need to know really something about the world. If you have a effector that does not contain the sensor, as we have when we look at a scene and we take our hand to grasp an object in the scene, then it's a little more complicated. You have to already combine information from different locations. Look where your hand is, look where the object is. You could still use control strategies, just making that distance small and steer your hand into the object. And therefore, it is actually not really theoretically different. It's just maybe not so immediately obvious, and you still have to have the same kind of stability property. And you know, for instance, that some patients who have cerebellar damage or Parkinson's patients actually have a hard time stabilizing goal-directed reaches. There has been a theoretical attempt in neuroscience to say, okay, that's control, and then there is some central level where we can think about plans as more static objects that don't have to have these properties. These would be the movement plans, for instance, and therefore, offload the stability just to the periphery. But we know that that's not true in nervous system. That's true in a lot of technical systems. For instance, conventional industrial robots can be programmed in a way that doesn't really talk about stability, and the control takes care of the stability. But organisms are not like that. One experimental signature of that is so-called online updating. Any time during a goal-directed movement, you can and actually spontaneously will update your movement plan to accommodate a change. For instance, in the environment, you can make the target switch to a new location, and you will update your movement plan. You have a delay of about 100 milliseconds doing that, but it's involuntary. For instance, it even occurs if you don't see that jump because the target jump was made while you're making a saccade. You're blind during the saccade, so you don't consciously notice the change, but your trajectory will curve at the right time to go to the new target. And generally, whenever a process is linked to sensory information that way, you need stability. If not, you will not track that change of input. In more psychological terms, you can also think of stability as the capacity or the need to suppress distractors. For instance, if you reach to an object, let's say you want to get the green cup, and there is another cup of a somewhat funny color here, you don't want to get distracted by grasping that just because it's closer to your hand. That might seem trivial to you, but we know from frontal brain patients, for example here, that they can't do that. They get distracted by that. When that cup is in a reachable position, here, some subtle difference, ignore that. So in some circumstances, they cannot suppress that response to the sort of the imperative stimulus, and they will reach for the wrong cup. Or if there's an open door, they will walk through it because it affords walking through it. It invites them to do that. So they have a difficulty stabilizing action goals against alternative distracting action goals. That just reveals that, in general, it's a problem to keep your action goals stable. I will, in the end of my talk, I'll show that that's the generic property of sequence generation. Whenever you're doing sequence generation, you have to stabilize what you're currently doing against the next thing that you will have to be doing soon, and only initiate that next action when you're done with the previous one. And that is a challenge when an action might take variable amounts of time. So that's about stability. Now, if you think about decisions, many of us think of decisions as the minimal thing for cognition. You at least need to be able to make decisions. And decisions, in some sense, intuitively, always involve a discontinuity, where something, the state before versus after the decision, where there's a qualitative change. For instance, if you initiate an action, that's a decision, and before you rest and then you move. So make a qualitative change in your behavior. Or you select a saccadic target or select an object which to grasp. Before you have two choices, then you have only one choice left. And you decide maybe to buy a car or whom to marry. You, again, maybe have a couple of choices and then change So that qualitative change is in contrast to what the notion of stability suggested, where in stability you have a graded change and you react to it in a graded way to return to the state you previously had, like when you're doing the movement itself or when you track something, when you make a pursuit eye movement. So there is, in a sense, that graded change that stability involves is violated in a decision. You could say that a decision involves an instability, that is, the processes that have resisted change when they were stable now have to bring about change. So they have to be released from stability. If you didn't release the process from change, you will not be able to make that qualitative change, to make the switch. So you could say that an instability, a release from stability, is a prerequisite to bring about decisions. It's the mechanisms through which that comes about. And I will now argue in 2 or 3 slides that instabilities are key to decision making, or more generally to flexibility in embodied cognition, both in the sense that it's efficient, you bring about change through instabilities, and it is necessary. That is, if you look at change, it is always accompanied by instabilities. Here, just a mathematical, making it mathematically concrete. Again, this system we looked at previously. Here was the attractor. Now, decision-making or instability always involves some change of the dynamics. That can be graded change. Here I'm suggesting that I'm adding some input. That just means I'm lifting this dynamics up, higher rates of change in a graded way. I've just drawn here three examples of what could be a graded change. And it will lead to a qualitative change. As you see, the attractor here will move a little bit to the right, so we'll be tracking that as the attractor changes, until it collides with this funny thing. This is a repeller. If you think of the same logic, it's something where if you're to the right of it, you have a positive rate of change, so you're going to move further away, increase to larger rates. If you're to the left of it, you have a negative rate of change. Again, you move away from it, so it repels neighboring states. When these two collide, as they did between these 2 slides, the attractor is annihilated. This is the so-called tangent bifurcation, the simplest and most generic instability that you can get. And there's no attractor left here, so at this stage, your system will just run here off to the right. It will go to maybe some other attractor you have somewhere else. Stability is a local property, and you lose that property of the state, and then what happens depends on what else you have in that system. That's the mathematical concept. This equation doesn't capture that because it has only the linear part. It's only the black line here that is described here. Here, to make that concrete, here an example from robotics. A very simple form of decision making is if you have a target, you have 2 obstacles. Should I go through them or should I go around them? Now, a very simple sensory motor decision. And you can literally operationalize this, and we do this in some robotic systems which we built this way. We have a dynamic system of heading direction. This is the heading direction, the heading direction of the robot. This is its rate of change, so it's just the turning rate of the robot. You can bring about by setting different amounts of voltage to the motors. And the dynamics of that means that the heading direction, the rate of change is a function of heading direction. Here this, I don't know, magenta line makes an attractor at the heading direction. That these brown kind of, or orange lines make repellers at the directions where these obstacle lies. So positive rate of change here, the attractor negative rate of change. The black line is just the sum of those. It has 3 attractors here, negative slope, and negative slope. These are the attractors going straight through, going around this way, and going around that way. 3 possibilities. Which one of those you will choose depends on your initial heading. As headed now, you will be close to this attractor, and you will just stay in that attractor. If I move these 2 obstacles closer to each other, you see these curves overlap more. The black line now has a single repeller in the middle and has only 2 attractors left. So now it will have to go around these 2 ways. And that just comes from instability. What happens in there is that these 2 repellers collide with this attractor. Here is the parameter, that's the distance between the obstacles. These 2 repellers collide with the attractor and make a single repeller, while the outer attractors are just gradually shifted. This is the pitchfork bifurcation, another very elementary bifurcation that just happens when you have some symmetry, when they are moved simultaneously in here. And that's how you make that decision. It's just to make it very concrete. If you don't follow that so quickly, there is a big literature on reading up on that. It's no mystery. It's a very standard thing. Here's a biological example of doing that. This is old work I did with Scott Gell so many years ago, where we looked at the coordination of rhythmic movement. So generally, if you look at rhythmic movement, there are always two patterns. You either synchronize in phase, like this, or you alternate. Like in walking, you alternate. And if you think of in gallop, for instance, you have approximate synchrony. In trot, you have alternation. You switch between those. And generally, the anti-phase type of pattern is unstable or less stable. For instance, if you go with a metronome, that would be an example. If you anti-phase with a metronome is syncopating, going off the beat. And if you speed up the metronome, sometimes done by music teachers to test your ability, then at some point you fall in with the metronome, you go to in phase. And experimentally, you can do that by having people make an anti-phase pattern. For instance, the fingers are ideal because they are minimal mass, so there are no mechanical problems. You just look at the coordination per se. And you speed up by some metronome the movement, then you observe at some point, for instance, at about 2.5 hertz, people can no longer do anti-phase, they switch to in-phase. And you can look at the stability by measuring, for instance, how variable they are in their performance. Here's the variability in in-phase as you increase frequency, here's the variability in anti-phase. Increases, and that's a signature of the loss of stability. The system becomes less resistant to stochastic perturbations. And only as you switch to anti-phase does the variance go down again. You can more directly measure the relaxation time. That's how long it takes to come back to the pattern when you perturb it mechanically. You literally have people move in an apparatus and you mechanically perturb the finger. You don't rip it off, but you perturb it hard enough so that they get out of the phase rhythm. And then it takes longer to return to the anti-phase as you approach the transition than to return to the in-phase. So this is a signature of actual loss of stability as you make a switch. Now this is an involuntary switch. It's just you're at the limit of your stability. You can't do it. You can actually also ask people to voluntarily switch, to just do in-phase and then you tell them, now switch to anti-phase, or do anti-phase and say, now switch to in-phase. And what you find is that the stability of the patterns, the intrinsic stability, affects that switching process. So for instance, if you switch from the less stable pattern from anti-phase, from the more stable pattern to the less stable pattern, that would be from in-phase to anti-phase, your switching time, that's the amount of time it takes to bring about that switch, is much more broadly distributed with a larger mean, takes longer on average than if you switch from the less stable to the more stable. That's faster and less distributed. And theoretical account for that uses the dynamic system account predicts that. Actually, it was a historical prediction in a sense because we did the experiments after doing the model. So stability is a factor in voluntary decisions, in intentional change of behavior. It works with it. So I'm saying stability brings about that change, and when you bring it about, you're sensitive to the stability of these patterns. And more generally, you can say once you have brought about a decision, a change, it is still required that you then stabilize that new state. If not, your decision itself will not be really a stable process. And here's a sort of intuitive illustration. If you have two choices, you have some activation field, and if you were just to do some readout level decision, just looking where the maximum is, or some thresholding, suggested here by some threshold layer, then noisy signals would fluctuate between these two choices, and you would literally change your opinion every moment in time. So what you really need to bring about that decision stably is to select one and then suppress the other, and that means really stabilizing your decision. I'll show you examples of that a little later. That's stability, instability. Let's talk about representation for a moment. Think about a simple scenario. You're grasping an object on a table there. I drew this by hand on some couple of objects. You're looking at that scene and you close your eye and you grasp your cup. You can all do that. Maybe don't do it with a glass of red wine on a white tablecloth, but you will be able to do that fairly well anytime. And that means that you're now reaching under a representation, that is something which we call usually working memory or scene representation, supports that reach that's usually supported by your direct sensory input about the scene. You can replace it or represent it by some other process. And that we can, of course, very commonly do. And it is not that this is a very qualitatively different thing. There is a continuum in the nervous system, in the processes underlying that, as well as in your behavior, between using the real-time sensory information and using represented information in that way. For instance, there's a whole line of work where people intermittently occlude an object, even in catching, where timing is important. You can occlude the ball at different points in time, and you can pretty much do that perfectly well. I'm not explaining the details of that, but pretty much there's no difference between seeing the ball all the time and only seeing it intermittently. So you can update anytime, but you can also substitute the online information by your memory information anytime. And okay, that's a property. Now, say, you know, why do we actually need representation? Do we really need that? I think Pfeiffer sometimes made that argument. It's not a literal quote, but he used to say, let's use the environment as itself as a representation. Look it up in the environment. And then that's a very valid point that we're actually trying to use a lot in our embodied systems. But it's naive to think that that does not involve cognitive processes, because to effectively look something up in the environment, you actually need support. You need some form of scene representation that guides your search. If not, you would each time have to make a new visual search, discover where something is in the environment, and we can do this, of course, much better as humans. We look up already in a very directed way, and then we update as we look there. This example, there's a huge literature on scene representation in humans. Andrew Hollingworth does very interesting work that when we work with him now from the University of Iowa. And here's an example where you're exposed to a scene, a laboratory kind of scene, different objects on the screen, and then you have tasks as detecting change, like this object has changed orientation. And you look if you detect the change when the scene is unchanged, when the scene as a whole has shifted, or when the object has shifted against the scene, or the scene against the object. And you're really much better when you're in the scene and you're actually insensitive to shifts of the scene as a whole. So you're the same in these two conditions. And you're really meaning that you're anchoring your perceptual context to be that scene context, and you're doing that in a reference frame that you can update between different views. And then, of course, my last argument for representation would be that learning is all about representation. And I'm not talking about, again, maybe at some very high level people might still argue about that, but the basic learning processes, habit formation that William James thought was the most fundamental form of learning. We know that is true. My own work in the development domain has been about perceptive reaching, where we can literally see how babies build up a habit to go to a particular location A when they're exposed to that several times, such that when they're then cued to a different location B, they instead go to that location A, and what they're literally doing is building up a habit to go to that location that can be measured as a pre-activation or a bias to select in the competition that previous location, which is also, actually we can also ask which coordinate system that is. And the opposite of habit formation, which is habituation, habit formation is doing the same thing again, habituation is avoiding doing the same thing again, can be looked at in very similar ways as building a representation that can replace the sensory information, stand for it, but now it acts inhibitorily. So for instance, in all these, this is only for those who know that, for instance, baby habituation experiments where you expose them to different stimuli, for instance, a drawbridge that moves in a particular way, and then when you show them the same again, they will be inhibited and no longer look at it so much compared to when you show them a new drawbridge. And you can literally say it's a question of how metrically close you are to the stimulus you got habituated to, whether you get released from that inhibition or not. So representation, again, very much like neuroscientists think of it as neural activation that could have been brought about by a stimulus, but is kept around somehow by a learning process, or in this case, a habituation process, and then can keep acting on the perceptual or motor system as if the stimulus was still around. And that's the sense in which I will be using representation. And I expect this afternoon we'll have a heated discussion about that concept compared to classical cognitive science kind of concepts. I want to close this general part of my presentation with the conceptual part by making it concrete. How could we actually assess whether a particular theoretical account or a particular model fulfills these constraints of embodiment? has these properties of embodied cognition. And very simple idea. So one thing is to probe whether the models that you're looking at can be enacted. Can they be linked to actual sensor and motor systems, maybe real sensors? Is it, well, what's in that link? Are there very non-trivial processes that we have to put into those links? And can they actually generate the behavior in time? You might know there are some models in, for instance, connectionism, where there are neurons that stand for objects, and you're accounting for a paradigm that's saying when this is object present, that neuron is on, or this, this letter on the screen, that neuron is on. And there, every engineer knows it's not a trivial task to get a system to respond selectively to particular objects on the sensor array. That's the whole problem of object recognition, has to confront invariance properties. So there you have a non-trivial interface. If you have a model that just takes, let's say, just luminance values or contrast values from your visual array, and you can drive your model that way, then you have a much better sense for being enactable. And a lot of the discourse, for instance, that Rolf has emphasized is about making this link to the sensory surfaces at a low level, where you don't hide a lot of cognition in the interface that you didn't account for. Autonomy is an aspect of that. Autonomy means you can ask, is my system one that just sits there and waits for a stimulus to then give a response, or is it a system that actually actively controls its perception, that autonomously in time drives its own behavior? Something you can look at. Is it flexible in timing? That's an aspect of that. Is a system acting out a fixed score? If you perturb it will just keep doing what it ever did. Take any industry robot. If you perturb it, it will just keep doing its thing and destroy everything that no longer fits. Or is a system capable of adapting to environmental conditions? For instance, when something takes longer, just hold on and wait a little, and then continue with its action sequence. And finally, you can ask, is your system capable of learning from experience? Is it open to learning? These are sort of four kind of benchmark, more conceptual kind of benchmark things for looking at models with respect to whether they are embodied or not. You could see that there can be some physically embodied systems, like conventional industry robots, that do not fulfill these tests. Right? So it's not just a question of if you have a body, it's a bit more conceptual issue. Okay, now I think I took about half my time, or is it less than half my time?
Actually, you have about 15 minutes.
50 minutes, that's fine too. So now I will show you the real, how we actually do that, the theory part, and I'll have to just give you a taste for that and won't give you all the details. I'll say that the theoretical language that I'll propose must address these issues, must address stability, instability, linked to these sensory motor surfaces and accommodate learning from experience. And the thing is that the theory I'm proposing for that is dynamical field theory. And I'll just tell you briefly what that is. It's a branch of neural network theory, a particular class of neural networks that starts by thinking about the things you want to represent in neural networks. We call the sensory motor surfaces, the space, or the feature spaces we'll be looking at. And as I hinted earlier, with stability, you need to have some metric in there. You have to say what is close to each other in representation. That's why we think of that as continuous dimensions. For instance, it could be just stuff homologous to the sensory surface, which could be often space, retinal space, allocentric space, or the motor surfaces could be saccadic endpoint, or movement directions, movement parameters, the vehicle's heading direction, but also more abstract things, like visual features, colors, orientation, mechanical features like impedance, or could be more abstract. I'll show you one example, hopefully can show you that ordinal space, where you express where something is in a sequence. That would be a space that is a bit more abstract. And so what neural field theory does is uses a space code in these spaces. Space code in the neurophysiological sense, that is, you have some activation defined over the spaces, so that every, if you want to think of a location, that would be every neuron, or every activation variable stands for a particular value. The peak of activation, therefore, stands for those values along the dimension. If the dimension is retinal space, it would be literally this location in the retinal space, or this movement command that's stored here. While where the activation is low, then you're saying that is not currently my percept or my motor plan. That's how fields represent stuff, essentially by peaks of activation. this is a neurally connected to copulation code. Those who know anything about that will know that in many cortical and some subcortical structures, neurons respond very broadly to varying motor or sensory conditions. These are neurons in motor cortex that very broadly respond to different directions of movement of the end effector in outer space. And from populations of such broadly tuned neurons, you can construct so-called population distributions of activation that are not distributions over cortex, they are over the parameter space that this piece of cortex represents. For instance, here over the movement direction. You do that by taking the so-called tuning curves of the neurons, combining them in some linear form, and then you can estimate what this population thinks about, for instance, movement direction. In fact, you can even time resolve that by using the current firing of these neurons to estimate that distribution. This is one example. You can do that pretty much in every sensory motor array. I'll not go into that very much. It's just where these ideas come from. And what we do then is we have a language in which we account for how distributions of activation like that evolve in time. This is what we call neural dynamics, or the dynamics of neural fields, and it has been pretty much this form I already suggested initially, that minus U term, and has some interaction. Interaction meaning the evolution at different locations in the field depends on what happens elsewhere in the field. There are really two forms of interaction that are critical. Local sites excite each other, local excitation that stabilizes peaks against decay, and field locations that are far from each other inhibit each other, negative rate of change. And that prevents the peaks from diffusing out all over. And together, these two forms of interaction make for peaks as stable solutions. I wanted to spend just a moment, running short on time, but I just think that's instructive. I'll just show you a computer simulation that illustrates how decisions and stuff like that are now made in this picture. Here you see on top, the blue is a field. This is the field dimension. There's some noise on it. It fluctuates. And behind it, the green is the inputs to the field, the resting level in the inputs. You'll see the green only when I change it a little bit. First, I want to turn on interaction. This is illustrated here at the bottom. This is the interaction kernel. This is over the distance in the field. So any location excites its neighbor and inhibits everyone else. This will not change. So what I can show you now is that in a field like that, I can induce inputs. You see here the green line. The blue tracks the green. It's an attractor. If I change the input, it tracks it. If I push it through 0, an instability occurs where this is sort of the off state. Nothing is excited. If I push it through 0, then that off state becomes unstable. It switches to a new state, an on state. This is a decision. We call that the detection decision. Now you have a supra-threshold peak. The red is all the positive parts of the activation through a sigmoid. Only positive parts of the activation play a role. You can see now there's more excitation here than input. It's self-excitatory. It's really good to call it a different state from the state before, and everywhere else the field is inhibited. That this is an instability can be seen from the fact that when I remove input a little bit again, like this, where I previously didn't have it, the peak persists. Actually, so at these values, the system is bistable. It can be either on or it can be off. And which of it is depends on where you come from. After you have initiated a decision, you'll stay on. That's how you stabilize detection decisions. And there's some psychophysical evidence. We actually do that. When you're off, then you need more evidence to sustain a detection decision than you need to maintain one. That has a limit, so at some point there's the so-called reverse detection decision where this will be gone again. This is when you will lose your detection per se. Another function of this is selection. I have here another input at some other field location, and now this input was selected over this one. This one is suppressed. The only reason why this one was selected over this one is because it came here first. That's the general principle of how selection works in the nervous system, that time differences translate into decisions. If you're first, you can first start to inhibit the other one, while this one, when it's below the activation threshold, it cannot conversely inhibit the first one. Could demonstrate that by just reversing the order. Now I give this one a chance, and then add the second one, and then it will stay in this state. It will stabilize the decision, in other words, and again, it translates a time order into a selection order. There's a limit to that. If I give one of those much more power than the other one, At some point it will switch. That's the selection instability, when your bias becomes overwhelming, and then you will stabilize that decision as well. And there's also something about working memory that I'll skip here because that's not so relevant. But I want to make one last point, is if I have what this whole way of looking at neural networks is a way in which you're always thinking of interaction-dominated states. These peaks are really, as you saw, dominated by interaction. They're no longer dictated by input. And what that does, it amplifies small input-driven states into macroscopic states. And I can illustrate that by saying, if I have some homogeneity, there's a little bit more activation here and here than everywhere else. Like from learning, for instance, through learning, these synapses are more effective, and you have a bias toward these locations. You can amplify that into a macroscopic difference, for instance, by just boosting the field, not giving it any information about where you want to build a peak, and then we'll build a peak at one of these two locations. Which one is now maybe determined by noise, because, or if there's an asymmetry, one of those would be large. And that's how you can bring up again instances from learning into real-time operation. There's a lot more that one can squeeze from these fields, but maybe that's enough for now. And I'll go back to, this is the advertisement I'll make in a second. Okay, so I'll show you that in this language, peaks are units of representations. They are attractors of neurodynamics. Therefore, they embody this stability property. I can link them to sensory information. And their appearance or disappearance comes about through instabilities, which then give us these elementary cognitive functions: detection, selection, and the last one was essentially what recall is about. So what I wanted to do in maybe the last 10 minutes or 5 minutes I have.
About 10.
Yeah, that's, my students will be sick when they know that I left so little time for their actual work. I'll just give you some little highlights of how to use this to now build embodied cognitive systems, just using this language. I'll just really flash that through. I want to go through 3 examples. I don't know if, I'll just show you the results. Scene representation, grounded spatial language, and sequence generation. Here's a new architecture. We just submitted this latest version, but we have an earlier version published, of a scene representation system that takes a visual array, puts it into a retinal system that's just a 2D spatial picture. It has also a variant in which one of those can be selected by inhibition, just like I showed, where you select a single one of these objects. You have a second layer that's of the same kind that is in an allocentric frame. We make a coordinate transformation to an allocentric frame. Again, you have multi-peak. This is then a working memory of the scene. And here you add a feature value. We add the feature value by, from the selected object and look up its feature values. In the simulation it will be color, but you can actually, no, in the simulation I'll show you it will be a label, because in this simulation we're adding a object recognition system that estimates at the same time a pose of the object. I can't explain that so quickly, but it's using also dynamic fields to do that. Estimates the pose of the object and the identity of the object. And so we're representing the identity of the object as a label dimension over the spatial dimension. Here's just to give you a bit of a flavor, an example of that. The camera input is here. The camera, actually in the actual system there is an active camera. The camera will be looking at different scenes. This is all just running now continuously. That's the autonomous here. Right? There's a dynamical system that just runs, and as it gets this input, this is the foveal image that will be driving the selection field. It's always adding then peaks to the spatial map. The spatial map is independent of the retinal transformation, so it's always the same. This is where the table is always in the same array. So after scanning the scene like that, it will have a spatial map and an associated semantic map. The different heights here where this red color are the different label values that were recognized for the foveated image. And this went a little bit too quickly for you to follow all of that, but the important message is you cannot build a scene representation autonomously. It's just running automatically. There's nothing there where you initiate something or determine something. And as a side effect, you can actually do online stuff. Like here, somebody is reaching in and moving the objects around. That will affect them spatially here. There will be some distraction here while the hand is in here, but because the hand is not in the database, it's not an object that's learned, it will not be recognized, and it will not be entered into the semantic map. It will not show up, so when the hand is removed in a moment, you will see that all the detractors are gone. And the system has been able to track what is where. It just tracks space, but it will in the end still know what is where because it carries along the label information. And you can do the same with a robot hand, which is not so important. Just a quick flavor. You can build embodied cognitive systems this way. Here, this example, I wanted to show two aspects about this. This is a system that grounds spatial language. It has, again, a camera image. Uses this is a 3D field that has color and then 2D, and you could write this as 3 slices through a 3D field. It has a target and a reference slot, and then a coordinate transformation where the target field is transformed into a reference frame that's centered on the reference object. And in this object-centered field, you can now apply spatial operators to decide what it means for something to be the left of something or something else to be on the right of something. You see that always involves coordinate transforms to apply spatial language like that. And of course, it implies bringing one object into the foreground compared to every other object. And then it implies applying the comparison operator. Now, I wanted to illustrate these first two things. You bring an object into the foreground really just by what I just called recall, but it's not from memory, it's from the scene. You have a scene like that, and you could just give a boost to the green slice through the 3-dimensional field, and that will mean that this green object has a chance to build a peak, and by boosting the target field, it will be considered to be a target object, and that's how you've sort of brought into the foreground. It's essentially a visual search, brought into the foreground the object in question. Here's a neural way to do the coordinate transform. You have the target representation over retinal coordinates, the reference object in retinal coordinates, and then if you think through that, a 2D field like that will project out the target object in reference-based in coordinates that are centered in the reference object. And this is illustrated here. You'll have 2 targets on the retina, 1 reference object. They build these peaks and build this reference-centered representation. If you shift the gaze, the reference object is now somewhere else. This stays invariant and it predicts actually where it's on your retina. Now, that's a very general tool that's been used by other people like Puget, for instance. And then you can apply these operators. The operators are just particular kernels where you're sensitive to where in a kernel your object lies. I'll skip over that. And then a system like that can do things like answer a question, where is the green object relative to the red object? You boost the green to ask that question, you boost that it's a target, and then you ask the question, you boost red and boost the reference field, and it will then be able to respond as the outcome of this operator that it's on the right, for instance. Or in an example here, which object is above the blue object? You boost blue and characterize it as a reference object, and you boost above, and what the system then will do is, after it gets a boost for target, it will select the target location, and then will activate the color of that target object, and will say it's the red object. And you can even do something fancy like, where's the green object, where you expect it itself to find a reference object for that. So it has to decide whether it says it's to the left of the blue or to the right of the green, and it will, through a similar sequence, in the end, come up with an answer that it took the blue object on the right and it says it's to the left of that, it's to the left of the blue object. That's what the system autonomously does. These kind of models can be compared to human psychophysics. We did something like that, but you can also use it to guide robotic interfaces. And in the last 2 minutes, I'll just point to the need to now make this autonomous. In this example I just showed you, the different fields have to be boosted to translate the parsing of the language to the system. So when you say relative to, then we said this is a reference object, now we boost the reference field. How to do that autonomously is the final topic is really how to do sequences autonomously. And Lydia Zanemiska in her thesis proposed something for that. And the idea behind that is that you have another kind of field that is now organized along an abstract axis of ordinal, the serial order of objects. So there's a dimension here of ordinal organization. And this particular field, we sample it discretely, but you could think of that as a continuum as well. And what then these fields project onto other fields that represent whatever is there at that particular order. So if the first, let's say for instance, the first action is to search for a particular color, then this will be a field over the color space that will specify that color, and then in a later stage you will be searching maybe for the green color. There's some motor and action systems connected to that, and critically there is what we call a condition of satisfaction field. So that's a system that will be sensitive to sensory information that tells you that you now achieved what you just previously tried to do. That can be something from the environment, like if you're searching for a red object, it tells you that you now have found a red object. Or it can be something internal, like if you're saying, I try to boost my reference field, I'm trying to now enter a landmark, then it can be just sensitive to you having done that. You actually now have a peak in your field that represents landmarks, and you say, I'm done, I have a landmark stored in my system. So it could be internal or external. Now, I usually walk people through that, but you don't have to understand the details. The main point is that it all just works with these instabilities we're just talking about. For instance, when a particular action is on, it induces a peak in the action field that specifies what action you now want to do, and that is just going through a detection instability. It also primes the condition of satisfaction to already have kind of pre-peak, but not yet the peak. It will need a second element. And then a peak like that will again act onto a field that does perception. For instance, when you're expecting something blue, it's the same visual search, only when a blue object is visible, then it will generate a peak and guide your robot to do that. And then, for instance, when the blue actually turned out to be green here, when the green object is really looming large, then that will boost the condition of satisfaction field enough to build a peak there, and that will then actually inhibit the ordinal fields, inhibit that. As a result, these peaks will decay, so that's reverse detection instability. You see that here, this is the condition of satisfaction peak, and that makes the ordinal fields to all decay, and therefore this peak decays, and therefore this peak decays ultimately, and when that happens, then the ordinal system is released from inhibition, and you build a peak again. You can't follow that so quickly, but I'm saying it's all the elementary instabilities, the three ones I showed you, all of those, correctly combined, make that this system then does a sequence, and we can test that. This is an example. The robot has three kinds of actions it can do. Look for colors. It has an arm and a gripper, and you can give it different orders, like to look for something red, raise its arm, open its gripper, close its gripper, and so on. Program, in a sense, by teaching different sequences like that. And then what will happen is that any time it gets a sensory signal, like here, that action was achieved, it switches the system to the next action, and then the corresponding action field guides the action of the robot. I have a movie which I could close on that shows a simplified version of this. This is a version where the robot only runs around. I can accelerate that a little bit. This is Julia actually teaching the robot these different colors. You can't see the colors very well. Showing different colors, and the robot is supposed to then search for objects of that color in the arena sequentially. And therefore, for instance, ignore a block of a color it is not currently looking for, only drive to that if it is the color it is currently looking for. And we took that task because this is a very primitive robot that doesn't know anything about the environment, makes a random search, and therefore it will take a variable amount of times for the robot to find one. The first was yellow, and here it finds the yellow right away. I think then red was found next. And there's an example now. I think the next was was it blue, right? Or was it green? I don't remember, but it will be ignoring, I think it will be ignoring this one because it wasn't of the correct color, and then we'll be searching for a long time to find the object of the right color. I think that's what's happening here. It's ignoring the blue one because it isn't yet there. I mean, believe me, this works. Here's a summary of that. Here's the teaching phase, and this is the production phase. And you see there are various amounts of time that searching for each of these colors takes, and the robot is able to keep in mind where it was in the sequence to not be, unlike the prefrontal patients, this is not a robot that gets distracted because there's another color that it might now be, that it could just take because it's later in the sequence. Okay, this was a rough ride through a few examples just to get you a little bit of taste. I'll conclude by saying that embodiment, in my view, is a theoretical stance rather than just a question of being an action system. It's a stance that recognizes that cognition is linkable to the sensory and motor surfaces, or must be linkable to these, unfolds in time on the background of behavioral environmental context. It's embedded in learning and background knowledge. And therefore, embodied cognition, I argue, it really requires stability, but also then actually instability, really, because you're making that claim of stability. You need instability to do decision making, and you need representation in that sense of representing the inputs. And the dynamic field theory is our proposal for a theoretical framework for how to do all of those things. And most of our work is about accounting for experimental signatures. I've only hinted very, very little at that. We work with psychophysicists in detail to try to make predictions about the experiments. And I've also showed you that these architectures meet the embodiment test that I have myself proposed, of course not by chance. They can be enacted on artificial embodied cognitive systems. They are autonomous, as I showed you the flexible timing in the last example. And I didn't show you so much the learning, but actually in the system I showed last, the sequence is learned through a very simple learning mechanism, leaving a memory trace in the system. So where we're heading, I don't think it's a fad at all. I think embodied cognition has changed our view of cognition, and we cannot now continue as before, even if some of the initial newness maybe of the embodied demonstrations is gone. We now will have to pursue the goals of cognitive science, but differently. We'll have to see how we can achieve the seemingly disembodied cognition now in a way that is grounded, is directly connected to the sensory motor systems, and then we will have major progress. For us, our local program is to go to things like object learning, behavioral organization, problem solving, but I'm sure for many of you it can be more ambitious things like even language or thinking itself. That will be our ultimate proof of embodiment. If we can have these principles in a robot, then we can actually think. Thank you.